In this lecture, we will talk about BCD to Excess-3 code conversion. The outline of this lecture as follows. First, we will learn about the code conversion, why we use the code conversion. Then we will talk about BCD number, binary coded decimal number. These are the binary codes corresponding to decimal number. We already learned about the BCD number in the starting of our course. In the starting lecture, we have learned about the BCD numbers. After this, we will talk about the truth table for BCD to Excess-3 code converter. Then using this truth table with the help of Karnaugh-Map, we will simplify the truth table for BCD to Excess-3 code. Then we will get some simplified expression. Those simplified expression will be used to design the digital circuit. Further, in this lecture, I will try to use the digital boards to design this converter. Further, to understand the truth table and the K-map, which is used to design the BCD to Excess-3 code converter. In previous lectures, some students have complained that they are unable to understand the lectures on these slides. Therefore, I will try to use digital board to construct truth table and the Karnaugh-Map, so that it will become easy for you guys to understand this lecture. Okay, now first let us talk about the code conversion. Why we use the code conversion? Because different digital system use different codes, and we have already learned about different types of codes. Those were BCD, internal code, ASCII code, and Excess-3 code, and so forth, and some different types of code we have learned in starting of this course. So different digital system use different codes. Sometimes the output of one digital system is the input of other digital system. Therefore, we use some code converter to make the system compatible. So therefore, we are talking about the code conversion. So first, so after this, let us talk about the BCD number. Binary coded decimal number, these are the binary number corresponding to decimal number. You guys already know about the decimal number, and decimal numbers are from 0 to 9. Those are 0, 1, 2, up to so on, up to 9. So there are 10 decimal number. Those are starting from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, and its base is the 10. In similar fashion, we know that the binary number are 0 and 1. Our digital system only understand the binary language. They understand 0 mean the switch is off, and 1 is the switch is on. Now corresponding to these number, I mean, if I want to describe these 9 numbers, so how many binary numbers are required? So if here we have 10 decimal number, so corresponding to each decimal number, we assign the 4 binary bits. So corresponding to 0, we assign 0, 0, 0. So this is the LSB, least significant bit. I am using here LSB. This is the least significant bit, and this is the MSB, most significant bit. Hope you guys understand here. It is difficult for me to use this digital circuit, digital board. So for 1 we have this bit is 0, this is 0, this is 0, and this is 1. For 2 we have 0, 0, 1, 0. So this is 2 raised to power 0, this is 2 raised to power 1, this is 2 raised to power 2, and this is 2 raised to power 3. So then for 3 this is 0, 0, 1, 1. If I want to convert this, these binary number to decimal number, I know that this its power is 2 raised to power 0, which is 1. So this is equal to 2. So 2 plus 1 is equal to 3. So for 4 this is 0, 1, 0, so on. For 9 BCD code would be 1, 0, 0, 1. So if we have some decimal digit or some decimal number, suppose 45, and I want to convert it to BCD, its base is 10, and I want to convert into BCD. So corresponding to 5, my code will be 1. So first most significant bit is 0, 1, 0, 1. This is equal to 5, and corresponding to 4 there would be the 4 binary bits. So I can write for 4 0, 1, 0. So this is the BCD code corresponding to 45. I hope you guys understand the BCD codes. Now let us talk about the truth table for BCD to Excess-3. So let me construct the truth table for the BCD code. BCD to Excess-3, I am constructing here the truth table for BCD to Excess-3. So here I have BCD number, so here first I have some BCD number. So those are, this is A, this is B, this is C, and this is D. So these are the BCD number, and here this is the input I will use as input. So here is the output. So the output is, I have again 4 number BCD to Excess-3. So for Excess-3 I have output as X, this is Y, sorry, let me start with the W, X, Y, Z. Suppose these are the output, W, X, Y and Z. So corresponding, when I have a number 0, so I have a number 0, then corresponding code would be 0 0 0. So when decimal number was 1, I use BCD code 0 0 and 1. For corresponding to number 2, when I have decimal number 2, its BCD code is 0 0 1 and 0. So for 3, this is 0 0 1 and 1. When the decimal number is 4, so this is 0 1 0 and 0. For 5, the BCD code was 0 1 0 1. For 6, it is 4 plus 2 is 6. So remaining are 0 bits. So for 7, then for 8, then for 9. So for 7, it's 4 plus 3, this is 4 2 plus 1. So for 8, this is 1 0 0 0. For 9, I can write 1 0 0 and 1. So in the previous lecture we have talked about the don't care condition. So the remaining combination, we know that there are the 4 bits here, we have 4 bits. So we have only 10 combination. The remaining 6 combination, 2 raised to power 4 is have 4 bits have the 16 combination. 2 raised to power 4 is equal to 16. So the remaining combination we will use as a don't care. So the output for Excess-3, I will add here 3, then I will get Excess-3 code. So by adding 3 in 0, so I will get the output would be 0 0 1 1. So adding 3 in 1, the output would be the 4. So I can write it 1 0 0. So this is the output for 0, this is for 1. So corresponding to 2, it would be 0. So 2 plus 3 would be equal to 5. So 1 4 plus 1, here I will add 0 and this is equal to 1. So corresponding for 3, when the input is 3, I mean BCD which is equal to 3, so the output Excess-3 would be equal to 5. Would be equal to 6. For this case, it would be equal to 0 4 plus 2 6 and this bit would be 0. For 4, when BCD is for 4, I mean For this case 4 plus 3 is equal to 7, so I will add 3 in 4, so this is 1 plus 0 1 1. For 5 it would be equal to 8, so I will use here 1 0 0 0. For 6 BCD code for 6 I will add 3, so the Excess-3 would be equal to 1 0 0 1. For 7 it would be equal to 8 plus 2, which is equal to 10. So what I am doing, I am adding in this, I am in BCD code, I am adding 3, so I will get the Excess-3 code. So this is BCD code, this table, and this table is for Excess-3. Hope you will understand my writing. So for 8 this would be equal to 1 0 1 1. For this combination for 9 it would be equal to 8 plus 4 12 and 0 0. Now in the next step what I have to do, I have to construct the Karnaugh-Map by using this truth table. I will with the use of Karnaugh-Map I will simplify these expression. So I will get some simplified expression, then I will apply those expression to design the digital circuit. So now I will use this truth table in K-map to get the simplified expression that I will use for that will use to construct the digital circuit that will convert BCD code to Excess-3 code. Now these are the outputs corresponding to these inputs A, B, C, D. This table is the input table. So here these W, X, Y, Z are the outputs. Now I will simplify these outputs. So you can consider it as a function. I mean these are the inputs A, B, C, D and their corresponding function. So you can consider these are the 0 0 0 0 0. I mean these 1 1 1 1. These are the min terms corresponding to these inputs. So you can consider W as a function. So now we will use Karnaugh-Map to simplify this function, this W. So next, okay, let us talk about the Karnaugh-Map. Here let me construct the Karnaugh-Map. So there could be there are 4 inputs, so there could be 4 cross, sorry, yeah, there could be a 4 cross 4 boxes. Okay, yes, let me construct it again. Okay, so this is this function W. I am going to simplify. Here I will use, so here is the CD and here is first 2 bits B, So next, so here C is 0 and D is 0. So you know the rule. So next I will change one bit. So here I will use C prime D. Then I cannot change this least significant bit. I can change this bit. So the next C into D. So here I will use 1 0 C into D prime. So first 0 0, then 0 1, then 1 1 and 1 0. So now look here, I mean this table, this column. So for when A, B, C, C and D are 0, here I will incorporate the output is 0. So when A, B, C and D is 0, sorry, A, B and C are 0. For this combination, W is again 0. Then for this combination, W is 0. So for this combination, W is 0. When AB is 0 and CD is 1, here I will incorporate 0. Now for this combination, A is 0, B is 1 and C and D are 0. For this combination, A and A is 0 and B is 1 and C and D are 0. So output is 0 for this combination. So the output is 0 for this combination. For 5, yeah, for this combination 0 1 0 1, this is equal to 1. For this combination 0 1 1, okay, 0 1 1 0, this is 1. So for this combination W is 1, 0 1 1 1, and again 1 0 0 1. So here is 1 0 and 0 1. For this combination W is equal to 1. So the remaining these terms, okay, no, okay, wait, then I think I lost, I didn't use this for this combination W is equal to 1. So 1 0 0. So here I will plug in 1. So the remaining 1 2 3 4, 1 2 3 4, these 5 and 6, these boxes, I mean I will incorporate here don't care condition. So here I am using the don't care condition x x x and x. So next what I will do, I will simplify this expression, this W I will simplify this function. So we know that we already know in when we have used in our previous lecture the don't care condition. These don't care condition can be used to simplify the expression. Otherwise we don't care, I mean we don't use in the circuit. So here we know these uh, these four boxes are adjacent. These four boxes I can use them. Okay, let me change the color. These four boxes are adjacent. So by simplifying these four boxes, so what I will get, I mean C prime and here C. When I will add these C prime and C, I will get 1. So I will get, here I will get D. So in this column, A prime A will cancel, so I will get B into D. So W is equal to B into D. Okay, so next, then these four boxes are adjacent. So let me use some different color. So I am using this yellow color. So when I will simplify these four boxes, so what I will get, I will get, I mean this D into D prime. When I will add these, so will cancel out. I will get C. Here I will get C plus C, and these boxes I will get C into B. I can write as B into C. Now these 8 boxes are adjacent, so I can solve these boxes. Let me use some different color. Okay, this green color I am using. No, this is the blue one. No, let me use some other color. So these 8 boxes are adjacent. So by simplifying these boxes, are this whole row, I mean these will cancel out. So I will get when I will simplify this row, I mean so here B plus B prime will cancel out, so I will get A. So the simplified expression, I can write it as A plus BC into BD. So this function W in the simplified form is equal to A plus BD plus BC. Next, for X, let me draw another box. So to simplify the output X, for X, so this is CD and this is AB. So okay, let me make it more obvious. This is for AB and this is for CD. Now when A, B and C, A, B, C, D are 0, so okay, let me fill this first. Here is 0 1, then 1 1, then 1 0, here is 0 0, then 0 1, then 1 1, then 1 0. So in this box, when the combination is 0 0, the output is 0. So when the combination is 0 0 1, in this case this is x is equal to 1. So for 0 0 1 0, this is equal to 1, and 0 0 1 1, this is equal to 1. Now for 0 1 0 0, this is equal to 1. So for 0 0 1 0 1, this is equal to 0. So here I will incorporate 0. So 0 1 1 0. So this is 0 1 1 0, this is equal to 0, and similarly 0 1 1 1, this is equal to 0. Now for 1 0 0 0, this is equal to 0, then 1 0 0 1, so this combination, this is equal to 1. So the remaining boxes would be don't care. I mean the remaining 6 boxes are don't care. So these don't care conditions, sorry, let me use this. Oh, how to undo? I don't know how to undo. Okay, let me capture the screen. So unintentionally I erase all these table, so I have no control on this, I mean digital board. So again I have draw these tables. Now for W, for output W, we got the simplified expression A plus BC plus BD. Now simplify the output X. So when I have combination 0 0 0, it is equal to 0. The output is 0. When 0 0 0 1, in this case the output is 1. Next for 1 1 1, the output is 1, as we sorry, for 0 0 1 0, it is output is 1. For 0 0 1 1, here output is 1. Next 0 1 0 0, in this case output is 1. Then for 0 1 0 0, output is 1. 0 1 0 1, in this case output is 0. Next 0 1 1 0, in this case output is 0. 0 1 1 1, output is 0. Next 1 0 0, the output is 0, and the output is 1. Sorry, here is 1 1 0 0 1. For this case the output is 1. So the remaining, here the remaining box are don't care conditions. Here I can put X X X. So these 6 box are for don't care. Now we can simplify this Karnaugh-Map. Here we can see these I mean this box can be simplified. Let me change different color. Again, it is difficult to select, so by using this box, these two are can be simplified. So I can write x is equal to here a will cancel out, I will get b, and then c prime d prime. So b into c prime into d prime. Next, I can simplify, I mean these two boxes and these are adjacent. So by simplifying these two boxes, so this a prime and a will cancel out, I will get b prime and this is b prime, and here this d plus d prime will cancel out and b prime into c. Expression is b prime into c. Next, I can say that let me use some different color. I'm trying to use different color. Okay, it's okay. These two boxes 0 1 1 1, and here these two boxes, these are adjacent. I can say these are adjacent. So by solving this, I will get the expression here a prime will cancel with a, I will get b prime, and here c prime will cancel with c, I will get d. B prime plus b prime into d. So here is the d. So this is the simplified expression for output x. So for output y, by looking at these min terms, so I will quickly fill this table. Here it would be 1, here is 1, here is 1, and here is 1, here is 1, okay, here is 0, here is 0. So this box is 0 and this box is 0, this box is 0. So the remaining boxes are don't care condition, so I can fill as a don't care condition. So now we can see that these four I mean this complete column, these four boxes are adjacent, so I can simply and these four boxes are adjacent, so I can simplify. So by simplifying this box, this complete, I mean this column will simplify, I will get c prime d prime. So y is equal to c prime into D prime. Then this column, again this will simplify, so I will get this is equal to C into D plus C into C into D. So similarly, when I will solve for Z, so Z would be equal to in this case it would be equal to D prime. So Z would be equal to, so I'm not solving, you guys can solve for Z. So it is equal to D prime. So next we have these four for output W, for this, for output X, for output Y we have the simplified expression for Z. So by using these expression we can construct a digital circuit. So here is the okay, let me erase this table. So here is the digital circuit. We have four, here we have four inputs A, B, C and D, and their corresponding, I mean Excess-3 code we will get at these outputs W. So W is equal to A plus B plus BC plus BD. So here it is equal to A. So from this AND gate I will get B, and okay, I will get from this AND gate I will get B into okay, so here C, I will get C, so here I will get D, so C plus D, then when it will AND with B I will get BC plus BD. So here I will get for X, I mean you can construct this digital circuit by your own way. So this X is equal to B prime C into this is equal to, sorry, this equal to X is equal to B prime, sorry, B into C prime D prime plus BC B prime C plus B prime D. Similarly this Y is equal to C prime D. So here I will get C prime D into CD. So this AND gate provide the CD, and this AND gate provide C prime to D prime. So I will get the output is equal to Y is equal to C prime D prime plus CD, and the output Z is equal to, which is connected here with the Z, which is equal to, sorry, this is connected with D, so this is equal to D prime. So that's it. Hope this lecture will works, and thank you.